Okay, so I'm going to continue with 2 or 3 more examples for today of invariant measures, of systems with invariant measures, and then next week we will start proving some results about the properties of invariant measures. So first, just want to notice that we have some simple generalizations of this. So suppose f of x is equal to 2x mod 1. And what does this look like? It just looks like this. Right? So obviously Lebesgue measure is also invariant. In this case, 3x mod 1 is the same. What is the topological dynamics of these systems, like this one here? Do you think this one also has fixed points, periodic points, and so on? Like 10x mod 1? What's the relation between 10x mod 1 and, say, 3x mod 1?
Maybe it's like the same, but with expanding in base 3 instead of that.
Exactly, very good. So if you try to multiply by 3 something that is written in its decimal expansion, you have no idea what goes on. But if you're clever and you write down the number in the base 3 expansions, you get exactly the same situation that we have before, right? So you see the fixed points, you see the periodic points. This is the shift, and the orbit is just the shift, right? So in general, if you take f of x equals ax mod 1, right, where a is a natural number, just write x naught in base a. Okay, then f acts like a shift, on the expansion, on the number, right? On the expansion. Okay. More generally, we define f. We define it on the interval. It's a little bit easier when you define it like this, but the interval and the circle are almost the same thing, right? So we say that f is piecewise affine. Piecewise affine if there exists partition P of the interval 0, 1 mod 0, so up to set of measures 0. So, but this can be a finite, it can be a countable partition, so into subintervals. Right? Such that for all omega, for all partition elements omega in P, f from omega to 0, 1, let's suppose they're open intervals. There's always, in these kind of things, it always gets a bit tricky if they're open intervals, closed intervals. So let's say into open subintervals, just to be clear, into open subintervals, such that f from omega to 0, 1 is affine. Right, so it has constant derivative. So the easiest case to generalize this is just when you have, so this is not 2x mod 1, but of course you don't need to make the partition the same. You can have just 2 elements of the partition, but one is here. This is affine, and this is affine. It's Lebesgue measure invariant here. calculation do we need to do here? Okay, I will leave it as an exercise that it is. Yes, it's actually easy. You just, because these two slopes are kind of complementary, right? So if this is a certain slope, this one is fixed, this is P, this is length P, this is 1 minus P. You can calculate the slopes and you can easily calculate the sizes of the pre-images and so on. Okay? What is interesting is that this holds no matter how many branches you have. Doesn't matter if the orientation preserving or not. So you can see again here, you can calculate these points, you can calculate these lengths, and you see that Lebesgue measure is invariant. And what is even better is that even if you have a countable partition, Lebesgue measure is still invariant. Okay? So this would be, I will leave it as an exercise again. It's a nice exercise. And superposition. F is piecewise affine. Implies that the Lebesgue measure is invariant.
So it's like a request that each interval goes on to
With constant derivative. Yes. Affine bijection. Yes. Yes, sorry, that's what I meant. Yes, full branch. Yes, so sorry, I should have written. Yes, so usually I call it a full branch piecewise affine. So by full branch, I mean that each branch is surjective onto the whole space. Yes, that is a very crucial point. Of course, these things are absolutely false if it's not full branch. You get all kinds of things. Okay, well, we will see. I will do a couple more examples. But first of all, let me notice that what we're doing here, at the same time, I'm trying to show that there are lots of examples in which Lebesgue measure is invariant, which shows that it's significant, but it also shows the limitation of what this implies, right? Because these are completely different dynamical systems. I mean, to have this system and this system, you take a point here, you take the same point here, it will do something completely different, right? So this is where really, when we look at the statistics for all these systems, we're going to prove the theorem that we proved about 10x mod 1. So it is not enough for the Lebesgue measure to be invariant. We're going to need to assume that the Lebesgue measure is ergodic also, which is something that a concept that I'm going to introduce next week. But using these two properties, we're going to imply that for almost every point, the Dirac averages converge to Lebesgue measure. In this case, in this case, in that case, in the circle rotation case, in all those cases. So it's a powerful result, but it also shows that the statistics only tells you the statistics, right? It doesn't tell you more precisely what happens. It's the power and the limitation of the statistical behavior. Okay, I want to look at two more examples. One of them is a generalization, so we want to move away from the piecewise affine case. F of x equals 1 over x mod 1. This is called the Gauss map. Has anyone seen this map before? Gauss map. And so what does the graph of the Gauss map look like? has these different branches. So basically you take the graph of 1/x, which goes like this, and you pull down the branches like this, right? So here it's something like this, and then here. So this is the part of 1/x that actually goes from 1 to 2, right? If you just look at this map of 1/x, and then here it will do something like this, and then here between 1/3 and 1/4, do something like this, and so on, right? And this has infinitely many branches, but they're not affine. It is not piecewise affine map. So using this map, you can construct, so just a little parenthesis, which is a side remark, okay, is that if you think of the map 3x mod 1, right, and we said we took the base 3 representation, right? And the base 3 representation corresponds to the orbit of the point in terms of this partition here. Right, so here you have a partition into 3 intervals, and then when you write the base 3 representation, 0.21, 0, 1, 1, 2, 2, 2, 0, right? It's just three digits. It's telling you every time you have a 0, you're in here, right? So this is like I0, this is I1, and this is I2. And if you think about it, when you have the digit 3 representation, or the same with the decimal representation, when we started with the decimal representation and we're trying to understand the orbit. But if you want, you can go backwards, right? You can start with the dynamics of the point and you can construct the representation, right? Because if I now take a point and I tell you what the dynamics of this point is, I recover the representation, right? I do a coding. This is called a symbolic coding. So I take this point, and I know that this point in I0, and then I know that its image is in I2, and the next image is again in I2, the next image is in I1, and if I know the infinite orbit in terms of this partition, then I construct exactly the infinite expansion of that, right? So I've coded the point according to its itinerary with this partition, okay? So it's interesting is that this is something we're not probably going to have time to investigate, but this is another very big field of analysis of dynamical system called symbolic coding, in which you study dynamical systems exactly by this. You take a partition and you code the orbits of points according to the elements of the partition, and this is an example in which that gives you a lot of information, right? If you do it in this case, you end up exactly with the base 3 expansion of the number, and you know that way which points are periodic and so on, okay? So you can actually do the same thing here as well. But here you have an infinite number of points. We call this I'm not sure if we want to call this I1 or I0. I think we want to call this I1, I2, I3, okay? So you take a point, x naught, and you look at its orbit, okay? And this gives you a coding. But this time this coding does not have just a finite number of digits. It has an infinite number of digits because this point could land anywhere here. And the coding that you get is exactly the continued fractional representation of numbers. I don't know if you're familiar with the continued fraction. So this is another way of representing numbers, right? You can represent them with the base k expansion, or you can represent them with the continued fraction representation. And it turns out that this Gauss map, that's why Gauss was interested in this map. In fact, he was interested in the continued fractional representation of this. But the reason why we're interested in this map is because Gauss showed he computed exactly the invariant measure for this, which is not Lebesgue measure, of course. Like you can see that you're not going to be likely to have Lebesgue measure, because if you take a set A, then it will have an infinite number of components which have finite measure because they will be small, right? So, but depending on where you take it, if you take something here or something here, clearly the derivatives will change here, so you will get different sizes, right? So you cannot expect Lebesgue measure to be invariant in this case. But what Gauss showed is that you can define this measure mu, defined by mu of A, is equal to 1 over log 2 integral of 1, so integral. So if A is an interval AB, so take an interval AB here. Take interval AB, 1 plus x dx. So I don't need to do it for interval. I could have just done it for the measurable set is the integral of A of this function. And this is actually explicitly equal to 1 over log 2 log of 1 plus b over 1 plus a. So there's a very specific formula for measures. And we can check that this measure is invariant. So maybe I would leave you to do it. It's in the notes, but you just check it. So this is a formula for all intervals. So here you can calculate explicitly the pre-image. So you actually know explicitly, because this function is given explicitly, right? You can find out all these intervals here are all of the form. The pre-images are what is it? 1 over m plus b. So pre-images are equals 1 over m plus b, 1 over m plus a. Right? Because when you apply 1 over x mod 1, you get a and b here. So they're all intervals of this form, so you can just calculate the measure of each one of those. You can sum them, and you can see that it gives you exactly the measure of AB according to this measure. Okay, so mu is an invariant measure. Okay, and then finally for the last example, we're going to look at the map. I'm referring to a bit that I don't have here. So f of x equals okay, what I want is this map here. This is the map. I think we define it like this. squared. So this is a map. It is a map from -1, 1 to 1, -1. So when x is equal to 1, this is, I'm sorry, the problem is that I realized that the definition of this map is somewhere else and there's about 3 different ways of writing, yes.
Not minus, sorry, it's just minus.
This should be plus, yeah. Yes, this should be plus, but there's other ways of writing the same number, and I can't remember which one we want for this example here. They're all basically equivalent. But this one, I think, is this graph here, right? So this is
Minus 1.
2x squared minus 1. Yeah, the problem now is I'm worried that I'm going to give you not the right definition. Okay, let me say what the concept is, and then we'll look at the notes and see exactly the definition. But the concept is the following: is that we have here the tent map, which is a map from 0, 1 to 0, 1, and it is piecewise affine with 2 branches of different orientations like this. This is affine, piecewise affine. Okay. So so this map here, let's call this one G. This is called the 10th map. This is the point 1/2. So for this map, Lebesgue measure is invariant. Okay, this is one of the examples we did. Even though the orientation is different in the 2 branches, it doesn't make any difference. This orientation is preserved. Now, these 2 maps have the property that they are conjugate. So we'll say in a second what this means. Conjugate. Okay. So I said that there's the middle part of the lecture notes. By the way, I don't know if you got an email, so I made a page on my website with the lecture notes and the recordings of the videos. So if you just go to my webpage, on the ICTP webpage, right, there's a link on the webpage, it says SISSA course, and you can go and then you get to the SISSA course, and I will be putting every week the recording of the lectures. You can download the full lecture notes, which I'm editing, so maybe don't print them, I'll be changing, updating them as I go along. And also there's a form just to register your name, so it's useful for me to know, to your know my name, so it's just a short form that you can fill in. Okay, so I think this is a good moment to introduce this concept because it will come in, it's an important concept. So we'll introduce it in a slightly more general setting. So here, let's suppose we have two dynamical systems. And then suppose we have H, which is a bijection. Right? And suppose that this bijection H has the property that it maps orbits of F to orbits of G. Right? So if you take the point X here, X0, it maps to X1, which is F of X0. And then if you take the image of X0 here, Y0 is equal to H of X0. And then you take here Y1, which is equal to G of Y1. Right? Then you want to make sure that H also maps the image of X0 to the image of Y0, if Y0 is image. So what this bijection does, it maps orbits to orbits, right? So we want this to be also equal to H of F this is G of y naught, and y naught is h of x naught, right? So what we want is to say that if you take a point x naught and you apply g and then you apply h, that is the same thing as applying h, you apply h and then you apply g, that is the same thing as applying f and then applying h. This is called a conjugacy. And it's not completely immediate, but you can easily see that, of course, this property continues, right? So if you take itlets, it will also be like this. So if you take Gn and Fn are also conjugate, because then you apply the same thing to x1 and x2, y1 and y2. So if you satisfy this property here, then what it really means is that it maps orbits to orbits. And it also means, it's easy to check, that if you take a fixed point here, it must also be fixed here. If you take a periodic point here, it must also be periodic point here, right? And then you can have various levels of regularity. So this is an equivalence relation on the space of all dynamical systems, okay? This is just really just the essence of this section on conjugacy that is in the middle of the notes. The nice thing is that this is an equivalence relation. It's easy to show because if you have another bijection that maps to not that conjugates these two, then you can just take the composition of these bijections and you get the conjugacy between those. So you get an equivalence relation, but then you can ask, okay, can we assume that this bijection is a homeomorphism? Or can this bijection be a diffeomorphism, right? And depending on the regularity of the bijection, you preserve more properties. So just with the bijection, you know that it will map periodic points to periodic points, but it does not imply that it will map omega limits to omega limits. Whereas if H is a homeomorphism, then it will also map omega limits. So if x naught maps to y naught, and then H will also look at the omega limit set of x naught, whatever that is, it will map exactly to the omega limit set of y naught. Okay? And if it's a diffeomorphism, then it even preserves more structure. And in particular, in our case here, we have that this is a C1 conjugacy. So C1 diffeomorphism. Even though it seems hard to believe, but in these notes, I'm sorry, I realize I shifted them around and I don't have it here. So I can't remember the explicit formula, but in this particular case, we have an explicit formula for this diffeomorphism. Okay? And so what we can do with this explicit formula is we can define you can push forward the measures from one to the other. I don't know if you're familiar with this idea, but you can take this Lebesgue measure and we can define a measure on this space here. So we write it like this. So definition. So if mx and my are the spaces of probability measures on x and y, right? And then H is a map from Hx to y. Define the push forward operator H star from the space of probability measures of x to the space of probability measures of y, defined by H star mu on set A is equal to mu of H minus 1 of A. So you say, okay, I have the C1 diffeomorphism that goes from this interval to this interval. Right? This is where this map is defined by that interval. So you have this map H, and then you take a set here A, okay, and you define the measure of this set A to be the measure of its pre-image under H. Right? This is a diffeomorphism, so it's an invertible map. So you take here whatever it is, this is H minus 1 of A, and then you take whatever measure you've chosen here. For example, here we could take Lebesgue measure of this, and we define, so by definition, the measure of A is going to be equal to the Lebesgue measure of H minus 1 of A. This is just a way to define a measure on this, okay? You can take any measure on here, and you push it forward in this sense by saying, you've got this map, you push it forward, which means you take every set here, and you assign a measure given by its pre-image, by the measure of its pre-image. This is a completely general and very powerful method, okay, for transferring measures. And then a lemma that we have is that this preserves invariant measures. If H is a conjugacy, so if H is a conjugacy, then H star maps invariant measures to invariant measures. Because the conjugacy means that it maps all the orbits to the orbits, right? And so this is telling us that if we have a measure here, right, the fact that it's invariant means that it has a relation to the dynamics, right? The key point about a measure being invariant is that it's a measure that is somehow not independent of the map path, right? It's invariant means it's connected to the map path. So when you have this conjugacy, you're also saying that there's a relation between the dynamics here and the dynamics here, so that there's a relation between G and F. And it turns out that when you take this measure and you push it forward here, if you think about it intuitively, it's believable. You now want to measure a set here, and you measure it by taking its pre-image here. And therefore, if you're using an invariant measure here, then the measure that you get here will also be invariant. This is the lemma, which again, I will leave as an exercise in the notes. It's not that difficult. You can think about it a bit. And so, okay, without giving you the details of the calculations, we can construct, we know that Lebesgue measure here is invariant, right? And in this particular case, we actually have an explicit formula for the diffeomorphism, and this gives us an explicit formula for the invariant measure here. And what we get is, because this is a diffeomorphism, then we get a measure that is absolutely continuous with respect to Lebesgue here. In fact, it has a differentiable density here, right? Because this is a diffeomorphism. So we have a very nice invariant measure. Otherwise, it's not at all obvious that there is such an invariant measure here, because this is not piecewise affine. There's not at all obvious what happens in this space. Okay, so I think this is more than enough for today. We've looked at, introduced the concept of invariant measure, looked at a lot of different kinds of invariant measures, right? Try to familiarize yourself with all these examples so that you're used to them. And then we will start on next week on chapter 15, which starts looking now at, once we have an invariant measure, it actually implies certain properties of the dynamic side. So far we've just used the motivation that every limit point of the Dirac averages is an invariant measure. We'll prove that fact. So next week we'll prove that statement that or sketch to prove at least that the limit points are invariant, and then look at the fact that invariant measures have many interesting properties. And that's where we really start the abstract ergodic theory. So maybe I'll take this opportunity to say something about why this is sometimes called smooth ergodic theory. In fact, what Stefano Bianchini will give next semester is basically also mostly smooth ergodic theory. So in, let's say, abstract ergodic theory, you just start with a measurable space, you assume your measure is invariant, and then you study all the different properties that you can get from the invariant measures. Whereas in smooth ergodic theory, first you have to find the invariant measure. So you have, in general, you have Lebesgue measure, like in this case we have Lebesgue measure, but then we use this information about the conjugacy to find the invariant measure. Right? So we're dealing with smooth systems. First we find the invariant measure, and then we apply the techniques of ergodic theory to invariant measures. Okay, whereas there's a whole field of abstract ergodic theory that just says, assume you have a measure-preserving transformation in abstract setting, and there's all the very abstract results about that. Okay, thank you very much for listening, and let me know, you can add me emails if you have any questions or any points, and otherwise I'll see you next week. Thank you. Oh, by the way, Dominic here, some of you have met, is a postdoc at ICTP. He works in dynamical systems. So he's very happy also to be a kind of tutor or reference point if any of you want some, also have some questions and want to talk to him during the class. Okay?
Stefano, is I don't know if I'm part of this online group as well, or I have to
There isn't yet an online group,
Oh, there isn't,
actually,
okay.
no. But maybe we can make one. I'm collecting, if you register on the form, then I will have all your names, and then we can somehow maybe figure out some way to have some kind